Good morning, everybody. Can everybody hear me all right? In the back, it's good? Perfect. So my name is Kyle Pucci, and I'm an applications engineer at ImageXpert Inc., which is located in the US. And today I'm going to be talking about drop watching, machine vision, and how these two can work together with Inkjet to help make inkjet development easier. So before I get into the details, I'll tell you a little bit about who ImageXpert is and what we do. So we're located in the United States on the East Coast, and we specialize in making drop watchers, printers, and inspection systems that are designed specifically for inkjet and also for a research and development environment. So the system here on the right that I'm sure most of you are familiar with is the JETXPERT. We have about 300 of these on the market, and this is our drop watcher for use with inkjet development. It's used in a variety of applications of inkjet, and for all these applications, the developers are interested in three things. They want to know when a drop is printed, what its velocity is, what its trajectory is, and what its volume is. And that's what our system specializes in doing. So what I want to talk a little bit about today is how you can use expertise in optics and also in machine vision to get very, very consistent and accurate measurements of these three things. So the three most important things that you have to remember when building a system like this is to include the following. So single event imaging, a short exposure time, and then what we call the double strobe method of measuring velocity. And I'll go into details about what each of these are. So single event imaging means that for every drop that you want a picture of, one picture is in fact being taken. The contrast to that would be if you're looking to measure a drop, you would take several pictures and perhaps add them together or average them. In a lot of cases, you would do this to increase the contrast between the drop and the background or something like that. But as you see for inkjet in particular, if you look on the right, the drops are not in the same place every single time. And when you add images together, it causes blurriness, it causes overlap, and overall this is not a very good way to perform a measurement of, let's say, the drop volume. Something like on the left with a single image for every drop will help you improve your measurements. The second thing is our short exposure time. And what this means is if you want to take a picture of the drop, the camera is open and the shutter is open for a very short amount of time. The reason being is these drops are moving very, very fast, often several meters per second. And the longer that the camera takes to take a picture, the further the drop is going to move and the blurrier it is going to be. So if you look at these three pictures, we're increasing the amount of time that the camera takes to take an image. And you can see that the picture all the way on the right, although it is the brightest, which tends to be good for inkjet, it's also the blurriest. So something like this would not necessarily be very good if you want to calculate the drop volume. If you want a very accurate measurement, you want a very short exposure time. And the third that I want to talk about is what we call the double strobe method. So what this means is if you want to measure the velocity of a drop, we actually take a picture of the drop at two different moments in time, the same drop. And what this allows us to do is measure the distance between those drops and then take the change in time, and that will tell you the velocity. So this is a little bit different from a traditional method of measuring velocity, where you will take a picture of one drop, and then you take the picture of the drop behind it, and compare the distance between those two to get the velocity. And I'll explain to you in the next slides what some of the differences are in why the double strobe method tends to yield better results for what you're looking for. So let's have a scenario where we have a drop traveling at 5 meters per second. So with the double strobe method, what we'll do is we'll take a picture of the drop and determine how far it's traveled. So in this case, after 100 microseconds, the drop has traveled 500 microns. Using the double strobe, we then take a picture of the drop again after a short delay. And so we measured the change in distance and the change in time. So we look, the drop has traveled 100 microns in 20 microseconds. So that tells us that the velocity is 5 meters per second, which is good. So our measurement confirms what we knew about the drop. So now let's look at the situation where the next drop is traveling at 5.2 meters per second. So we take our initial measurement, so it's this time's gone 520 microns in the same amount of time. After our delay, it's traveled an additional 104. And we look at the change in distance over change in time, and we get that this drop is 5.2 meters per second. So regardless of the scenario with the drops, the measurement is correct. So now we're going to take a look at the same exact situation using the more traditional single strobing method, and we'll see what happens. So our first drop travels at 5 meters per second. We locate its position. And now the second drop is traveling at 5.2, remember. So there's a little bit of drop-to-drop variation. So with 5.2 meters per second, we measure the distance, and you see the change in distance is 124 microns between the two drops, and the change in time is 120 microseconds. So if you use that as your calculation, you calculate that the velocity is 6.2 meters per second, not 5.2. And the reason that this is a problem is even with very, very small variations of the drop velocity, you're looking at this at such a short moment in time that any variation at all, when you extrapolate out to 5.2 meters per second, yields huge changes. So if you're interested in looking at practically what this looks like, this is data that we recorded from our most consistent print head that we have in our office. This one has the best jetting behavior. And so you'll see using the double strobe method, we calculate anywhere from 2.2 to 2.3 meters per second as the velocity of the drops. If you look using the single strobe method on the same exact drops, you see that the velocity varies anywhere from 1.8 to maybe 2.6 meters per second. So you can see how small amounts of drop-to-drop variation have a huge impact. So that's why all of our systems, we use the double strobe method, and we believe that it yields the most accurate velocities. So what we've done with our company is we've taken all of our findings about measuring drops, and we've integrated into them several products that are designed for use with the R&D environment. So I'll go through each one of these very briefly, starting with the smallest one. So this is the JETXPERT OEM. And this is designed to add these measurement capabilities into your printer or your dispensing system. It's about this large, and it's a fully integrated unit. So what you see here is everything you need. It has the computer, has the camera, it has the light source. And this can be dropped into any printer, and it will instantly add these measurement capabilities to your printer. A little bit larger of a system is the traditional JETXPERT and then the JETXPERT 2. And what these do is measure volume, velocity, and trajectory in one plane for the system on the left, and then in two planes for the system on the right. So you can see trajectory in the X direction as well as the Y direction at the same time. In addition to these systems, we have a variety of what we call add-ons, which allow you to automate processes, study things like latency or the change in frequency on your drop velocity, and all sorts of other measurement capabilities that you can build onto this system at any point in time. And then our largest system is actually a JETXPERT and a printer integrated into one. So this is designed for R&D, where you can go from visualizing the drops to then seeing what the impact is on that drop on the print quality. So you can integrate things like a print quality inspection system, drop weighing, all sorts of things into one system that's easy to use and quick to transition back and forth between the two. So at this point, I hope that you've learned a little bit more about what goes into imaging the drops. And if you have any questions, you can approach us. We have a booth around to the front near the drinks. So thank you very much.